Hey everyone, it's Paul Bertorelli reporting from Melbourne, Florida, where Florida Tech is. The airplane behind me is the Pipistrel Vellus. It's the world's first certified electric airplane. Certified in Europe, but not the United States, which is why it's here at Florida Tech. We're going to talk to Isaac Silver, who's overseeing a program here to develop data on the Vellus for the FAA to construct some sort of framework for electric airplanes to be certified in the U.S. Right now that really doesn't exist, and in fact it's not really in sight. We're going to look at the airplane systems, how it's constructed, and then we're going to take a flight in it. And by the way, that noise you hear in the background is the charging system. So let's get started.
Well, this aircraft is part of the flight test engineering fleet at Florida Tech. Flight test engineering is in the College of Engineering and Science as part of the aerospace engineering program. And 2014, 2015, we received a grant from the Bueller Foundation to build a flight test engineering laboratory. That grant money was used to purchase this aircraft along with a few other flight test aircraft. The flight test engineering program trains students to be flight test engineers, usually collecting and managing data during flight test. So being able to expose them to a lot of different airframes is important. Having the electric aircraft opens the door to that phase of the industry which is presently developing. So it's going to give the students an edge. You're going to get out there with more electric aircraft coming online in the near future, the near to mid future. They will have experience with the aircraft before they get there with this kind of technology. One of the other things that's happened having these assets, we've actually been able to pursue research funding, and we've been approached by groups to fund research, one being the Federal Aviation Administration. The FAA is very interested in getting baseline information on electric aircraft and gaining experience with them. So they have funded us to receive data from the first 50 flight hours and to bring FAA personnel into the aircraft to gain experience with it. They're basically trying to determine what's going to be required to certify these aircraft under the FARs. In Europe, this aircraft is certified for a flight time of 50 minutes with only a 10-minute reserve. In Europe, they got that through a special authorization. Here in the U.S., we're still limited to the Part 91 regulations, 30 minutes of reserve fuel, in this case battery power, at normal flying speeds, normal cruise speeds. So for us, that really limits us to about 20 to 24 minutes of flight time. Our flight profiles to date have been flying test cards where we go out and we fly a very fixed profile, and we're looking at how variables affect energy utilization, weight, temperature, other atmospheric conditions. And we have another test card where we're going out at different weights and we're seeing what kind of performance we get at different power settings. So we're really characterizing the energy burn and performance of the aircraft at this phase in a very regimented way, so we have usable data to ask the next questions. What we're finding is that with a single pilot on board, solo operations, we can get out there, fly for about 24 minutes on a low energy consumption profile, and we land with roughly 54 to 57% battery power, and the display is showing 30 minutes remaining. So that's 24 minutes of flight time light. It's down to about 18 minutes when we have two people on board. And it depends on the day too, but 18 to 24 minutes flight endurance with that 30-minute mandatory reserve is what we've been seeing.
Let's take a look at the construction and specs on the Velis. You may recall Pipistrel's previous electric model was the Alpha Electro. But the Velis is an engineering leap beyond that. It derives from this airplane, the Velis SW-121, which is a type certified aircraft, but which we would know in the US as a light sport aircraft limited to 600 kg or 1,320 pounds. In Europe, EASA has a certified category just for this. In the US, we don't, at least not yet. We have ASTM consensus standards. Both versions of the airplane are built with a combination of carbon and aramid fiber with a wet layup system and assembled in a new factory just across the Slovenian border in Italy. Showing its glider DNA, the composite work is just flawless, with all the control gaps tightly sealed to reduce drag. Both airplanes have high aspect ratio wings with full span flaperons rather than ailerons. This has one downside that I'll get to later. The high T-tail has a conventional elevator with electric trim. The gasoline version is powered by the 100 horsepower Rotax 912 certified engine, which, with 25 gallons of useful fuel aboard, delivers 5.5 hours of endurance with a 30-minute reserve. The electric Vellus has essentially the same dimensions, but the weights vary quite a bit. At 769 pounds empty, the gasoline SW121 is light, and that allows for a useful load of 553 pounds. That's two 200-pound people and full tanks. The electric version is 172 pounds heavier empty at 941 pounds. That leaves a useful load of 378 pounds, meaning a pair of 200-pounders will put it over the limit, and anyway, broad-shouldered people will find the cockpit a tight fit. That'll be worse in cold weather because the Vellus has no heater. And unique to electric airplanes, the weight they take off at is the weight they land at, so there's no option to carry less fuel. The Vellus is powered by a Pipistrel-developed E811 brushless AC motor, which the company prefers to call an engine. Regardless of what you call it, it's a remarkable power plant. At only about 50 pounds, the engine can deliver 65 kilowatts or 87 horsepower max, according to the POH. Pipistrel's marketing data pegs the power at 57.6 kilowatts or 77 horsepower. Either way, that's impressive power density. On a dry weight basis, the electric engine delivers about 1.54 horsepower per pound compared to 0.80 horsepower per pound for the Rotax. And like all electric motors, the Pipistrel engine has crazy maximum torque at 162 foot-pounds compared to 94 for the Rotax. And there's no waiting for that torque either. It's available instantly. But what electrons giveth, they also taketh away, and the piper to be paid is battery weight. The Vellus has two packs, one behind the firewall and one aft of the cabin. Each has a stated capacity of 11 kilowatt hours on a weight of 162 pounds each. But the actual pack capacity is probably closer to 12 kilowatt hours and maybe more than that. Still, when the battery weight is considered, the electric engine looks worse at 0.2 horsepower per pound compared to 0.32 for the Rotax with max fuel. Also, the electric airplane suffers in endurance. It's less than 20% of the gasoline version.
Well, we've got the cowling off and we're on the charger, so we can take a look at all the different components. The noise in the background is the charger, so sorry about that. Right up front, connected to the propeller, is the motor itself on this aircraft. It's an axial flux motor, AC motor, and it's just here, this little tiny thing that looks like a fat turntable is the motor unit. That's all there is to it. Everything else in here is support to power that motor unit. And up here forward of the firewall, we have the motor controller itself, and it's a three-phase motor controller that powers the motor. It's AC, alternating current. And down in the bottom, there's actually a radiator straight down, and there's an air scoop on the front of the aircraft. The motor is cooled and the motor controller is liquid cooled through that radiator, and here's some of the cooling loops over here. This is the charging port, and the charging port feeds back to the batteries. There's one battery right behind this firewall, there's another one in the tail. Yeah, as you can see, this system is liquid cooled, and that was a major step from their previous attempt, the Alpha Electro, and this aircraft. It came with a liquid cooling option both for the motor and the batteries. This motor and power system is a very mature electric aircraft system. Our experience operating it has shown that it has no real deficiencies and operates very well in the real world. The batteries are controlled via a battery management system. They're thermally regulated with liquid cooling, and it does a really good job. The batteries are very stable throughout all phases of flight, even on a hot day here in Florida. Those temperatures in the batteries and the motor controllers were some of the issues, the limiting issues they had with the Alpha Electro originally when they brought it over to the US. Let's go inside the aircraft and take a look at the rear battery module. All right. So you can hear the cooling pumps. They're running, there's a fan and a coolant pump that's circulating coolant into a radiator that's behind this battery pack, and it's drawing air through there to cool it. and that's what the sound is. So this is a good shot of the battery pack. The front and the rear battery pack are exactly the same. Right now the aircraft is in charging mode. It's plugged into the charger, so there's a charge status display here in the aircraft itself. Normally this is where the primary flight information for the motor would be displayed, the motor and battery system. So right now we're at about 80% charge. It is charging, and it shows temperature and other status of both the charger and the batteries during the charge. The aircraft charge is controlled by circuitry on board the airplane. So the aircraft could go to common chargers using a common plug, and the plug on this aircraft is actually a European standard plug. And in theory, the aircraft could control its charging process at charging centers out there in the world when the infrastructure is ready. Right now, obviously, it's using a Pipistrel charger, but ultimately it's going to have to be able to use whatever charger is available. With our typical flight time of about 18 to 24 minutes, we have seen charge times between about 1 hour and 20 and 1 hour and 40 minutes on the ground. So for a 30-minute block in the aircraft with 20 minutes of flight, 10 minutes of ground time, we need about 2 hours of service time to turn the aircraft around.
Now on to flying the Vellus, but first a word here about noise. You might think electric airplanes are quiet, and well, they are from the outside. In fact, they're all but silent. Inside the airplane, it's a different story. Although there's no exhaust note, the prop still sends pulses back across the windshield and windows with every rev. Actually, it's 3 per rev. This is what it sounds like. The intercom we had in the sample Vellus did a poor job of rejecting noise, so I'll apologize for the noisy audio. It didn't sound any better inside the airplane.
Okay, so Isaac, we've been over the systems in this airplane in detail, and now we're in it to actually fly it. Pretty simple, just flip on the master switch and the avionics switch.
Yeah, everything in this aircraft is pretty much an automatic self-check as far as firing the aircraft on. When we turned on the master switch, you saw the annunciators come alive. If those remain on, or there's some blinking codes or whatnot in the abnormal procedures, you can see what that means. But we have 2 more switches in the power-up sequence. One is the battery to the engine, and the other is power to the engine controller. So if we go ahead and turn on the battery switch there, that connects the batteries to the engine system, and the rest of this display will come alive.
Now I take it the avionics and everything else are running on their own separate bus, not related to the power.
That's correct. There's a little 12-volt battery which runs the ship. It's the main ship battery, and it's charged off of the engine power system when those batteries are on.
Okay.
So the system is coming online now, and if you go ahead and turn this engine power, the throttle is at idle.
Okay.
And that'll provide power to the motor controller. You can see all of our indications are now coming alive. We have 2 displays. This is the primary flight display. It gives you overall battery power remaining, expected flight time remaining, and it has gauges for the motor temperature, the coolant temperature, and then the individual battery system temperatures. On the next page, we have a little more detailed information. We have some information about cell health and the state of health of the battery. And you can see the minimum and maximum voltage on the cells within a battery, so you can tell if you have a problem developing based upon that.
Taxiing the Vellus is pretty conventional. It steers precisely with nose wheel steering and has a tight turn radius. According to the watt meter, it uses only about 1 kilowatt while taxiing. And once you're at the runway, there's not much else to do before you take off.
One of the things about this airplane, there's very few pre-flight checks. There's only one really, which we can do right here. And that is, we've already checked the flight controls, trims are set, we have to put the flaps in the first position for takeoff.
Okay.
We have to do a power check. And in order to do the power check, keep the wind noise down. We will hold the brakes, and we're going to advance the throttle and make sure we get at least 50 kilowatts.
Okay, and we're looking here for that.
Correct.
Kilowatts.
That's good. You can bring it all the way back.
Okay.
RPM was normal. It was in the normal range.
That really, the power comes up, it really feels like
Oh,
it's
yeah.
got punch to it.
And you've got more. That was only 50. You'll get more out of it for takeoff.
Yeah, we're total is 77?
Yep. We'll probably see 69 under a flight load.
Okay.
Ground experimental 880 Hotel Mike at the FIT South run-up pad with Juliet, taxi for a southeast departure.
And takeoff is a surprise. Earlier I mentioned how fast the torque comes up in an electric motor, and it comes up right now. There's no incremental winding up as with a gasoline engine. This causes a curious bobble right at rotation. It's best seen from the rear. Once the wheels let go, that torque impulse causes a roll and the airplane slides to the left. Isaac Silver warned me about it, but I still couldn't counter it on the first try. He said everyone who flies the airplane has the same experience. Another quirk that Vellus has is that to control motor temperature and minimize wear, maximum takeoff power is allowed only for 90 seconds. And because the airplane requires flaps for takeoff, the would-be student is confronted with both a power reduction and flap reduction right after takeoff. Once established in climb, the Vellus doesn't need much rudder and climbs about like any other Rotax-powered airplane. With those clear plastic doors, visibility is excellent. The Vellus is capable of 98 knots in level flight, just not for very long, at least if you want to get back to the airport. My usual drill is to do some steep turns, stalls, and other maneuvers, but it took 7 minutes to get to the practice area and at least that much to get back, so you're wise to pick an upwind practice area. Even then, range anxiety is as unavoidable as is obsessing over the battery capacity remaining display. Setting the power at 24 kilowatts gave a workable training speed of 85 knots indicated, and that's what you would probably use for training. The airplane has 22 kilowatt hours claimed capacity, but a 24 kilowatt burn is not really nearly an hour of flying time, but it appears to be quite a bit less. The battery monitoring system seems to be conservative about flight time remaining. At gross weight, our flight time was 21 minutes, and that burned 43% of indicated capacity. On paper, that's about 9.5 kilowatt hours. In fact, when recharged, the airplane absorbed 12.6 kilowatt hours. This suggests that either the battery monitor is not that accurate or that the capacity is actually more than the 22 kilowatt hours claimed. For pilots of electric airplanes, this will matter a lot. The Velis POH is festooned with warnings related to battery faults that could cause thermal runaways or automatic disconnection from one or both battery packs, like this one that says applying full power at a state of charge less than 15% could cause battery disconnection. Florida Tech's testing hasn't seen any of these warnings come up, but Isaac Silver says they may pose certification issues with the FAA. In any case, this is a lot for a student to manage, and pilots will have to master this stuff. Another quirk I mentioned before relates to landing the Vellus. The full-span flaperons mean that if maximum effort roll is needed, say in a crosswind, the high side wing will suddenly have less flap than the low side, and if the speed is between VSO and the clean stall, the high side can stall, causing a roll in that direction. Silver told me he had it happen once, and the only way to save it is with a quick stab of rudder. This may be more than a student can handle. For this reason, he recommended flying the airplane on during landing, as with a wheel landing and a tail dragger. We lack the battery capacity to remain in the pattern for more landings. So what to make of the Velis Electro? I think anyone who flies it will be impressed with the engineering and execution of the design. Pipistrel is way out ahead of other electric airplane companies. The Velis really shows what's possible, but it also shows what isn't. For US-style training, it simply lacks the endurance to be practical. Maybe it's different in Europe, but I don't think the underlying safety of a 30-minute fuel reserve should be chewed down to 10 minutes just to accommodate an electric airplane's limitations. We already have enough fuel exhaustion accidents without encouraging people to shave the margins ever thinner. And what's the trade-off here anyway? At $209,000 or 185,000 euro, Vellus costs more than twice as much as the Rotax-powered Alpha trainer. Yet it's really not practical for air work or cross country, so that means it could be a cycle trainer for landing practice. But that's only rational if the flight school also has a gasoline version of the same airplane. Otherwise, the Vellus is just too different from other aircraft to offer much training value. The Vellus's operating cost is a big plus. Our 21-minute flight consumed $1.26 worth of electricity, or about $4 an hour. A Cessna 172 burns at least $40 an hour in avgas. The Vellus's maintenance requirements are still a work in progress, but for now it needs a motor overhaul. That's just basically bearings and seals every 300 hours. The motor has to be sent to Slovenia for that. Pipistrel expects that requirement to ease as the airplane gains more operational time. Same with the battery packs. Replacement cost of those is $22,200, but it's not yet known if the replacement cycle will be 2,000 hours or something more or less. So operational costs here are really a moving target. In any case, because the airplane's capabilities are so limited, the lower operating costs can be applied only to a portion of the training, maybe that quarter or third of flying hours spent exclusively in the traffic pattern. So the bottom line is, given its limited endurance, the Vellus just isn't realistic for the US market. I'm sure it will find a few early adopter buyers interested in the technology and in low emissions flight, but for now it's best thought of as a technology demonstrator that opens the door to what's next. This technology has quite a ways to go to be as practical as a Skyhawk burning avgas. But it has to start somewhere, and the Vellus is at least that, a start. You can find a full report on the Vellus in the February 2022 issue of Aviation Consumer Magazine. For AvWeb, I'm Paul Bertorelli. Thanks for watching.